Hello, everyone, and welcome to this QuEra webinar introducing Kirin, QuEra's kernel intermediate representation compiler infrastructure. My name is Yuval Boger. I'm Chief Commercial Officer of QuEra. What that means is that the team and I work with customers, whether governments, HPC centers, or enterprises, to help them most out of their quantum journey. We work with them to provide on-premises or on-cloud computers to co-develop algorithms and do other research. So I'd welcome you to reach out to me. I'll type in my email in the chat in a little bit and would love to hear from you. Together with me is Roger Liu. Roger, hello, how are you?
Good.
Roger is the main event. I'll just provide a really quick intro of QuEra and why we're here, and then turn it over to Roger. I'll even turn my video off so you can focus on Roger and the amazing things that he's got to tell you. QuEra, for those that are unfamiliar, is located in Boston. We're based on, our products and our work is based on breakthrough science developed at Harvard and MIT, and of course also at QuEra. We consider ourselves to be the premier quantum innovation partner, helping you make the most out of your quantum journey. We build quantum computers with neutral atoms. Neutral atoms is one of many modalities that people use to build quantum computers. Some use superconducting or photonics or trapped ions and so on. And we believe, and more people agree with us, that neutral atoms are really the best way to get to large-scale fault-tolerant quantum computers. One of our computers is available on AWS, on Amazon Bracket, since November of 22. Has been used by hundreds of institutions worldwide. It's been the enabler of fantastic scientific articles, from string breaking to optimization to quantum machine learning. And on our publications page on the website, you can find many of these papers. QuEra is well funded. We recently raised $230 million, an investment led by Google and SoftBank. And we partner with enterprises, HPC centers, and governments to get them to where they want in quantum. Quantum computers are not there today. They're good for smaller problems. They're good for experimentation. They're good for learning. But many experts believe that in 2 or 3 years, they will be able to deliver true business value beyond experimentation learning. And we want to make sure that you are ready to make the most out of quantum computers, both by building the world's best and most powerful quantum computers, as well as working with you to help make the most out of them. Neutral atoms have several advantages. They scale to hundreds of thousands of qubits, tens of thousands or hundreds of thousands of qubits in a single machine. We use individual atoms as qubits. We pack them tightly, about 4 microns from one to another. So in a very small space, we can have many atoms. This is in contrast with other technologies that might require multiple network modules, which makes deployment expensive, power hungry, and very difficult. We operate at room temperature, which again speaks to both ease of deployment. There's no need for nightly gas deliveries. There's no need to build a football stadium with cryogenic cooling. We just operate at room temperature. We move our qubits around. I'll show you a video in the next slide. And that means that we can take any 2 qubits and basically bring them together. When they're close together, we can make them interact. And that all-to-all connectivity, the ability for every qubit to interact with every other, makes algorithms shorter and more efficient. We also have what's called parallel operations, where we can create a single operation can operate on multiple qubits at once. That's wonderful. These atoms are natural, meaning they're individually perfect. I could put 1 billion atoms together and they'll be perfectly identical. There are no manufacturing defects or variations to worry about. And we also have them in a way that has high fidelity in terms of low error rate, as well as long lifetime. So you can make really long and complex calculations. The picture that you see on the right is one of our most recent deployments. It's our Gemini gate-based computer that's based in AIST. AIST is the National Institute of Advanced Industrial Science and Technology in Japan. And so we are very pleased to have delivered that, and looking forward to continue to working with AIST to really help them achieve some fantastic results. I spoke about shuttling, and here is a video. Of course, this is dramatically magnified and dramatically slowed down. This appeared in a paper that was led by Harvard. It appeared in Nature at the end of 2023 and demonstrated logical qubits in quantum error correction. Each of these individual dots is an atom, and you can see that we can move them around. And when they're close together, we can make them interact. You also see in this video that in this particular experiment, there were two zones, a storage zone where qubits live for a long time, and an entanglement zone where we can actually create operations on them. And you see that shuttling, that movement between storage and entanglement. So quantum computers, or neutral atom quantum computers, have unique features, but to make them accessible to customers, there's a lot of software that goes into it. We need to be able to understand how to move the atoms, how to move them in a way that preserves their state, which atoms to move where, how to provide operations. So there are layers and layers of software infrastructure that try to mask that complexity so the user can get closer and closer to just saying, this is what I want to have happen. And then intelligent software translates it. And this is actually the subject of this webinar. At QuEra, we've been writing such software for several years. We've gone through several generations and iterations, and we came up ultimately with an open source framework called Kirin that's used to create many of these layers. And we want to share with you both what we learned and how you can join this open source project. Before I finish, I just want to mention that we'd welcome comments in the Q&A box or in the webinar chat. I'll try to ask Roger as we go along. But for now, Roger, the floor is yours.
Thank you, Yuval. I will share my screen. Okay. Thanks for the intro, Yuval. So today I will talk about Kirin, short for kernel intermediate representation infrastructure. This has been a compiler infrastructure we were using for our internal and external use of our SDK and compiler pipeline. So on the at the bottom here is a simple here's a QR code if you would like to check out the repo. And feel free to if you have questions later that we don't have time to answer during the talk, feel free to shoot me an email. So today so Kirin is an infrastructure for scientists. So today I'll go through the motivations, and also I know lots of you are not from compiler background, but physicist experimentalist. So we want to show you why would you need a compiler, and when do you need a compiler, and how could Kirin help you in that case. If we have a little more time, we'll talk about we'll show an example of a very simple quantum language created using Kirin in a few minutes. And then we'll briefly talk about what the next generation SDK of QuEra for quantum circuits and neutral atom, these all atom move architecture using neutral atom going to look like. So internally from QuEra, the motivation of having a compiler infrastructure is really because we have a long history of creating compilers all the way back to 2019. And there has been a lot of compilers built around different kind of intermediate representations used to represent the device. There has been many representation for the pulse level controls. So that is a list around 6 so far, I think. And there are many also. So 2 years ago, I started working on these atom shuttling based architecture, and so we started defining a lot of quite a few different IRs for atom shuttling. The problem is when people start doing research or just start finishing their work and define a new IR, there's always a good reason that they need to define something new, because some of the definition in the old representation does not fulfill the task. However, as a result, none of these compilers actually interact with each other. They don't. You have to keep rewriting duplicate works and ports from here to there. So this has been a tremendous issue for us. That the software has been very fragmented, and we cannot share anything in the end. So to build the infrastructure, essentially, initially was just to fuse, unify the representation into one for all levels. And I want to address this problem from a more compiler perspective. But internally in QuEra, just like everyone here, most people who work in the quantum computing field are not compiler experts, and we're like you. We're from we're trained as a physicist, or maybe we're trained as a computer science that works more on theory research. And in general, we see there's a growing need of compiler engineering, not just for quantum computing, and even you just want to do simulation like tensor contraction. There's a lot of intersection between the compiler theory, compiler engineering, and complicated simulation, or just controlling these new complicated hardwares at various levels. So a lot of scientists start touching compiler engineering, not just in the field of quantum computing, but also, for example, solving complicated ODEs requires some knowledge of the compiler, or even people working with automatic differentiation. A lot may need to learn a little bit about compiler. So before we dive into a more detailed introduction of Kirin, what that is, I want to briefly talk about why would you need a compiler? So many may ask why. So compiler usually is about compiling some defined programming language, and be it a generic language for arbitrary program, or a domain-specific language for example, just quantum computing, describing a quantum circuit. So then, so people would ask, why do I need this actual expressiveness? Why can't I program the controller in my experiment directly? Because these are really just a list of polynomials to form a positive. Or why can't I program a quantum circuit as a list of gates? So what's the benefit of more complicated structure and more sophisticated software to transform these representations? So before going to explain this directly, I want to tell you a little bit a short story in the traditional computing or classical computing history. So we know everyone today uses so-called BLAST libraries, which implements very fast primitives for linear algebra operations. And one of the linear algebra operation is the matrix multiplication that everybody uses in basically all the fields we probably have today in science, machine learning, quantum computing, solving ODEs, so back in 2002, when everyone was trying to optimize the matrix multiplication using compilers, Kazushi Goto wrote this Goto BLAST by handcrafted assembly code, which beats almost everyone's compiler, and that it was a very huge code base, and this eventually evolves into Intel's MKL library which is probably the golden standard for linear algebra implementing linear algebra operations. However, if you look at Linus' work in a few other high-level language community utilizing the compiler, especially the LVM tool stack. So, for example, in Julia world, the loop vectorization gaseous package using just around 2,000 lines of code to achieve similar matrix multiplication performance. Or if we're fine with sacrificing a little bit more performance, but with more but we want to import things easier. You can also write the same thing with around 60% performance with just 18 lines of Python code. So here you can see the compiler is really about how can we manage complexity using abstractions. Even the final artifact is the same. Even they're all just eventually going to be a list of commands. And this basically means that we can write less code if we have a good language and a compiler built for it. Moreover, because all the hardware we are using today, especially in the quantum field, it is rapidly evolving. Like in QuEra, we're pushing out this Gemini machine for digital quantum computing just 2 years after Aquila. So the ability to be able to transfer to compile code between every generation of machine without a big breaking change is also the benefit of having a compiler, because from the high level the code is it is less hardware specific, so it's easier to directly compile to a new architecture. So here I have two pieces of program to give you a little bit more concrete feeling what's the difference. So on the left-hand side is a classic OpenCasm2 implementation of quantum Fourier transform in the style of list of gates. And we can see, so from first glance, it's a lot longer than the program on the right-hand side, which is example program of extended Casm written in Python, where you can freely use for loop and recursions and control flows. So the left-hand side, we have a fixed number of qubits, because otherwise we can't fit in the screen. So you imagine if in order to program a full QFT program, it's gonna be a lot longer if, in reality, when you use a lot of qubits. So it's longer enough that it's impossible for human to write at. However, on the right-hand side, our program is just few lines and it's generic to number of qubits. So for people familiar with quantum programming, you probably you have probably seen the similar things like right-hand side a lot. So this is the benefit of expressing this. Even eventually, because of the low-level hardware constraints, we may eventually still lower this programming to a list of gates. But as a human, you can write a lot less code without repeating yourself. So the goal of compiler is to enable you to write less code, which means fewer human errors, and that also means a lot less work on testing things. So one piece of code works for arbitrary number of qubits and probably arbitrary type of device. But on the other hand, if we only have one single program to write, then there's no need of compiler, and you should just write whatever is available directly. For example, in our older our previous generation of machine QuEra, there was at beginning there was only global controls, so there's no need to have a complete compiler. you can just program the device using a few using 3 waveforms to control the global wave to do the global control. So what does the QC mean for folk software these days? So usually because now all the quantum power is marching towards quantum error correction. This essentially evolves the hardware to have a big controller in order to execute these QC cycles to do error correction and to run a decoder. And that usually means a more complete ARM or RISC-V or x86 CPU with more classical logic possible to execute on the device at real time. This also means we need to execute more complicated circuits, for example, 1,000 qubit times 1,000 layer gates. So for such complicated programs, very likely that a human will write less optimal program that is possible to implement on this hardware, especially given that not everyone is aware of what the hardware architecture is and what actually is faster on the hardware. So on the right hand side, I want to show you a very simple example of a dummy program where the circuit is implementing a more traditional style, which you can see in many SDKs like Qiskit, Circ, where we first define a circuit object like this, and then we keep pushing the gate into the list of into this list of gates. So here we can actually execute the control flow in Python, which is actually external to your representation. But this basically pushes a few gates into this circuit into this circuit. However, the following, if we want to do a conditional gate based on Merriman result, which is a very typical operation in quantum error correction. Because, for example, this here we detect the qubit has an error and want to flip the qubit back. So this operation is impossible to, written this way. So which of the results is if this is simply just a reset operation, people will just hard code this entire thing as a gate. But as a if condition, as a control flow, is not possible to do it in this representation because we need to know the actual result of this measurement to be able to execute this block, which is not available ahead of time. So this also means we need a representation of this type of control flows in the representation. So on the other hand, which is also some syntax you can see arising in a lot of SDKs. So we have this in Bloqade. You can also see it in, for example, Penlane, NVIDIA's QIQ, where instead we mark a Python function as a kernel function, which kind of means this function is going to be executed on the hardware. And here, these control flows are native representations of what's going to be executed on the hardware. The compiler will have the freedom to decide whether it's going to flatten these operations or keep it as it is and actually execute it on hardware. And this way, we have the native representation of control flows, which can be executed at real time. So this is this is the difference between external control flows and native control flows. So this is kind of the requirements. The QC poses us where if we want to more optimized program, we need to gather more information from the user, store them in your representation. So this could be an example that show you a list of gate is not sufficient to program more complete programs, and not just because of lack of abstraction and writing more code. However, the goal here is really not to create yet another way to represent quantum circuits. So in general, the more information we gather from the user input, the more things the compiler can do afterwards to decide how to do the compilation all the way to the pulses. So to summarize, so why would you need a compiler? So first of all, it allows you to write less code, especially when the program is large. Allows you to manage the complexity of writing many programs, and this by using abstractions and allowing you to compose program written by different people. And next is fewer errors. So it kind of stops you from fighting the hardware errors using compiler checks. And if you program a general purpose language, you will see these concepts like types and linters. These are the very common compiler tooling that help you check if my program is executable on hardware. And last is more performance. This usually comes last after being able to express a program, execute it. A compiler is able to find equivalent programs that potentially have better performance on a target machine. So that could be a quantum circuit with less gates, or a pause program with shorter pause, or an atom shuttling program with a shorter path to shuttle the atoms to the right position. So, and in which case you don't need a compiler, there's only one program or a few programs to write. And there isn't much complexity to actually control the hardware. So, for example, a pure analog device with only global controls, then it's a very simple program to comprehend for a human being. Then there's no need to write a compiler. I see there's a question in the chat. Oh, yes, Yuval. Okay, I'll continue. So, as I mentioned, so in our field, a lot of scientists is delving into the compiler engineering direction, just to get this work done, for the benefits I mentioned, like writing less code, more correct programs without worrying about violating hardware constraints. So what are many scientists looking for? Is something not in C++, definitely, and ideally in Python. Most people just program Python. And people are not aiming for compiling millions of IR nodes, because most of these programs are just a small piece of program calling maybe some other small piece of program, but they are usually embedding a big chunk of Python program, a normal Python program, that handling some other logic before running the device. And there's a lot of need to come up with a custom language. For example, MX Primal is working on new architecture is because of the new functionality device. It's naturally to insert new semantics to my language. So in order to program things easily, a low effort front end, like how do I actually write this the text of my program with custom both semantics is also preferred. Last, there are some common compiler passes, which I will briefly mention a bit later, but don't worry if you never heard about these words. So some common compiler passes is generic to any program, like constant propagation. These compiler passes are essential once you have like basic abstractions, or even you have experimental calibration and I get new calibration data, I want to partially compile my program. These compiler passes become very useful. But we don't want to keep rewriting them again and again. So we want to be able to share some compiler passes. And last, we want to have good composability for fast prototyping. In the traditional compiler industry, people address these problems. There actually this is called so there are actually a lot of framework trying to address these problems. So the most famous one is the MLIR from the LVM stack, namely the multi-level intermediate representation. And there's also a Python version of MLIR implementing pure Python called XDSL. And in more language-wise solution, there's a compiler plugin initiative in the JuLLM community, which is driven by more scientific software engineers. And some people also use Google's JAX, which not only provides an AD engine in Python, but also provides a generic way to transform Python expressions.
Roger, there's a question on slide 8 before you proceed, if you can address that. Someone from the audience is asking, I am confused with how the H gate is being optimized to run in parallel inside slide 8.
Oh, yes. So I didn't I didn't mention this. Probably was too fast on this slide. So for this particular program, because the H gate does not act on the same qubit. So this H gate essentially can be run in parallel if your hardware is able to do it. So this is a special property of Ripper Atom, is we can execute the same gate with in parallel. For example, we can execute these 4 H gates in parallel at the same time. But in terms of this program, we don't essentially need to unroll the entire for loop, but instead we compile the for loop into one instruction at low level. So this kind of goes back to the reason why we want to have a more structural representation in a program, because on the left hand side, because even this for loop is constant, which is equivalent to a list of commands, all you will get in the end from the compiler side that you will see is a list of gates. So then imagine this is not just 4 qubits, but like 1,000 qubits. You will see 1,000 H Halma gates on in your list. So figuring out whether this is a Halma gate applying to all qubits globally, it's gonna take O(n) number of time and this number of qubits. Where if this is a user written for loop, we know the structure already. All you need to do is look at the loop body is HI and the loop iterator is a constant range. The job is done. So this is the benefit of having a more structural representation, that not just recording the list of gates, but knowing a bit more about what you actually want to do. Hopefully this answers the question. Okay, so if there's some more question, feel free to ask a bit later. I want to finish. Want to keep up on the schedule. We're talking about some inspired work, previous existing work of Kirin, where we learn. So the problem we'll address here is a fragmentation of these representations of quantum circuits, pulses, atom moves, and even just classical logic. And there has been an existing solution from the compiler community, essentially coming from MLIR, where instead of trying to design the full language, we design the language in terms of small groups of semantics. So these semantics are like just puzzle pieces, where you have a small language for describing what is the if-else and what is a function, and I have small language describing what is a quantum gate. And once we have these, when we need a language that can execute quantum gates conditionally, we just need to compose quantum gates with if-else and maybe function together, and then we get a small language that can can describe the execution of quantum gates conditionally. However, why don't we just use MLIR or use these these tools born from more professional compiler engineering community? Is actually the question that I usually use this comparison. So I'm already designed for a fully fledged compiler that is not just for a small kernel program written in Python, but it's designed for basically building arbitrary compiler that is more serious. So you can compile C++, you can compile Rust or Julia, lower that into some MLR description. So it's like a very fancy car, like a F1 racing car. The complexity naturally arises from these very hard requirements. And it aims to compile millions of IR nodes efficiently. Where for Kirin and for our use cases in these experiments or quantum circuits, we're really not looking for compiling a large program or compile the entire C++. All we need is a small subset of Python embedded dynamically inside Python. So this poses a huge difference and allow simplification of a lot of design. Also, it has different requirements on sharing a set of tools, analyzing and representing dynamic programs in Python. So for MLIR, it's a very fancy car. Where for Kirin, it's a simple Toyota car that you maybe just drive for a few miles. And we want this tool to be built tailored for scientists only. We don't aim to build yet another MLIR. So later I will show you this. MLIR is actually Kirin is actually complementary to MLIR because of such compatibility. But let's go back to think about what we want. So essentially, we want something like this in Python, where in the quantum case, in the quantum circuits, we just want a simple language that defines a decorative Python function, where the decorator marks this function is not going to execute by the Python interpreter, but it's going to be executed by our hardware. And we would want to have some custom instructions that is not the traditional classical instruction, but some custom instruction representing your hardware execution. In this case, we want to allocate a new qubit or acting some gate. And the next, we want to have native control flows that follows the same semantics as Python, where so here you see is a if statement, which acts like just a normal Python if statement, where if you measure result is y, execute the ASCII gate, otherwise I will skip the ASCII gate and return. And beyond this, you may want the ability to compose different functions like this and call them. So what Kirin provides is a set of framework that allows you to get this almost for free once you define what instruction that is. And it will give you an intermediate representation that uses the most common, that is very similar to this MLIR infrastructure that is formalized in the so-called static single assignment form. So don't be scared by this terminology. This computer science jargon. So static single assignment, as the name says, so it's the only special thing about this representation is in this transformed intermediate representation program, every variable, for example, here the percentage, these names start with the percentage are the variables. So all the variable is assigned and only assigned once statically. So you can always you always know where this variable was created. The benefit of imposing this restriction is very easy to know how the data flows in your program. Because error variable is only created once, I can easily tell where this, how did I get this variable. So as a result, that allows you to easily, for example, figure out what are the dependency of my gates. If my gates does not depend on same qubit, then that means they can run in parallel. For example, or if my classical operation does not the output of my classical operation is not going to be used by any statement, is a piece of that code, I can just delete that. So this is what Kirin provides you, and this printing right here is what you see directly from the Kirin's pretty printer. So here we actually use a few dialects provided by Kirin on top of our own quantum dialect. You see here. So the Kirin provides some existing dialect handling the definition of functions, and this is the head of a basic block. So basic block is another special component in the assistive formalism. It represents a node that's a piece of a list of gates. In the quantum case, it represents a list of gates locally, and the last statement of a basic block always represents a conditional or branching statement, which where we will jump to a different basic block to implement the control flow. I see there's another question. Yes. So yes, what I this is only a toy language I show to you guys to help you understand what this compiler pipeline looks like. But the actual quantum language we use in our SDK is a lot more complicated than what I show here. So you might be you might find familiar of some of these concepts in a lot of existing implementations. Some of them use their own infrastructure, some of them use MLIR. Okay. So for example, you can implement a low level AFLs using a conditional branching, where if the measurement result is true, we go to the first block. Otherwise, we go to the second block, which skips the ASK gate. So next, I will. So since we still have a few minutes, I'll use 5 minutes to show you briefly what this demo gonna look like. So we'll probably not gonna cover the later interpreter part, but I'll show you how you define something like this from scratch in 5 minutes. So next I'll share my slide. I'll share a VS Code.
Roger, this is very interesting. So if you need to take a few more minutes to show the complete demo, then please feel free to do so.
Yes. Yeah. So first of all, I will just copy paste some stuff I already defined. So we're gonna use the so-called QLAX library to do the simulation later if we have time. But first, you assume you have some just some random runtime object or some random Python object you already have, like what is a qubit, what is the basis of a measurement. These are all just the normal Python objects. And then from Kirin, we import some basic tools to define the IR. So these are the modules we need: type slowing, as some declaration tools, the statement decorator. So the first thing we do is we define our dialect, which is very simple, just creating a object using the dialog constructor and creates the dialect. Then then we can wrap the normal Python type as qubit state type. This is our problem state. So simply we know that we have a new qubit statement where we create new qubit. So we can declare the statement in this way. It's like a normal Python data class. So there's some special field and types. So trace indicates some property of the statement. In this case, we allow you lower from a normal Python call syntax, which you will see what that means later. And states and it has input argument of type state, which we define here from the simulator, and it has output results type, which is of qubit, which is what we wrap here. So similarly, we can define the AST gates and CZ Hadamard measurement, etc. So I'll copy paste them here. So next, all you need to do is is define a dialog group, which is a group of dialogs. So here we only have we only define what the quantum dialog is, which provides the commands for running a quantum circuits. So Kirin provides you a built-in basic dialog, which contains the dialog group that contains the basic semantics for typical Python program. So we just add our dialog to the basic and create a new dialog called quantum. And this we can optionally run some compiler transforms here, but right now we're not gonna worry about it. And now we can use it directly. So if we have so now you can use this as a normal Python program, but actually will take over from Python interpreter and compile into this intermediate representation. So then you can implement, for example, compilation algorithms by rewriting this representation or running some analysis on this representation. For example, decompose a CX gate into CZ with 2 Hadamard, or replacing each gate with your pause routines, so we get a low level pause. So Kirin kind of handles all the basic tools that to implement all these tools. And here we see the linter has been yelling at us about the type issue. So actually, we provide some tools in the so-called lowering path that allow you to define the correct Python types as a wrapper. So you get free linter support from the you get free linter support from normal Python linters. So this still works as previously, except the linter also your Python linter also understand what these commands are. So we probably won't have time to go through everything, but so now let me keep going on the slides. So in general, what does Kirin do for you? It gives you a free front end. It provides a lot of commonly used compiler analysis and transform built around this so-called abstract interpretation concept. And using Kirin, we're building our next generation SDK for QuEra. That is not just quantum circuit. So right now we open source our quantum circuits circuit level SDK, which contains a small DSL called Queen that adopted from my previous work, YL. and also provide a few dialects for commonly used formats like STEAM and CASM2, as well as integration with circ. And this contains a fully featured CASM2 parser and tooling, and you can because the dialects are composable, you can easily extend CASM2 with control flows to get something like CASM3 or like a quasi CASM3. So for Outlook, the goal of Kirin is building a more accessible compiler infrastructure for scientists that focus on dynamic kernel functions in Python only, empower our SDK Bloqade from an infrastructure perspective. And our non-goal is not porting MLR into Python or implement a pure Python version of MLIR. And in fact, in the future, we may end up we may look into this direction that we implement part of a Kirin in a low-level language without breaking Python while still allowing to define the compiler from Python. And what do we offer in Extra in terms of MLR is composable Python lowering. You can compose your Python front end using different dialects, defining different dialects. And we also offer this after interpretation framework and analysis and dynamic functions that native to Python. So if you're interested in this work, please check out this repo, Kirin. And we also have open sourced our circular level SDK recently, and we're planning to also open source a few other levels in the future, be lower level than circuit. Yeah, if you like this idea, remember to start a repo to support us. And feel free to join the Slack discussion, GitHub discussion that we provide a link in the README of Kirin or Bloqade. We have so we can answer your questions from the Slack directly. Thanks for you all, and I will see if there's any more questions.
Thank you very much, Roger, for an excellent presentation. I think that what's important to realize is that we didn't set out to write Kirin as an academic exercise. This is, sort of we feel the scars and the pain and the tears of us having to write all these intermediate representations and all these multiple layers over the years. And so we solved the problem using Kirin. It fits very well into the eat your own dog food category. And we decided to open it up to the community so that other people can both enjoy this as well as contribute, use it for their own purposes, not just quantum, but could be HPCs or could be compiler infrastructure for science, and so on. I do have a question on the chat. Let me just read it out loud here. Thanks for the talk. This seems like a very useful tool. To what extent have you implemented dialects or libraries for higher level quantum error correction operations? For instance, are there built-in abstractions for tasks like stabilizer measurements or logical polygates? How would you like to answer that, Roger?
Yes. So we have a work in progress. We have some work in progress work in terms of QEC level representation. We hope we can give you. So right now, if you're looking at QEC representation, because we already defined dialect for STEAM, so if you want something today, you can actually program. You can actually compile things to STEAM directly using our circuit compiler, where that provides some basic definition for the QEC semantics like detectors. But in the long run, we hope we're aiming to provide tools to actually program a custom code at high level, as well as marking decoders, extracting decoder error models from high level natively using in our circular language. So these high level abstractions specifically for QEC will be kind of defining a separate dialect, and you can compose it with the existing circuit dialect. And in fact, if we once we open source some our lower level representations, the benefit of Kirin is you can also compose this QEC commands with our low level representation. So you naturally get some representation for the, you naturally get some ability to program QEC at low level.
Roger, what license is Kirin provided under?
The license Kirin is released is under Apache License 2.0 with the LVM extension, means that anything you compiled out of using Kirin, or that you compile out of this compiler build using Kirin is under your control. We're not going to claim anything of that. And for Kirin's code base itself, it's released under Apache 2.0.
Wonderful. I don't see that there are any other questions. So Roger, thank you very much for this presentation. Thank you everyone for joining us today. We have plenty of webinars almost every month, scientific, commercial, roadmap, and others. Feel free to join us. If you sign up to our mailing list on QuEra.com, you'll receive notifications on them. So thank you everyone and have a great day.